our topic is about AI, but it's more specifically about how to power AI, right? How can we deliver it reliably, both ends of the wire, super important, risk and reliability, and then just the total power consumption is amazing, the amount that it's going to take. So again, cost and availability, delivery is going to be a big part of the equation going forward for AI. We got to deal with all of these things, all of them together at once, and so it's going to be a big hurdle. And so we're going to talk about that just piece by piece, and let the experts here tell us how to do it. So I'll just start out with the easy ones, and I'll start out with you, John. With AI and EVs and widespread electrification surging, how do we balance grid stability with growing energy demand?
I think you've hit on a key question there. Grid stability is very urgent, because when you talk about data centers, and they are growing, and the amount of power that's going to be needed, we're using about 4 trillion kWh of electricity in this country every year. There are predictions that it's going to be double that, like maybe in the next 15 years. Well, where's all that going to come from? It's going to have to come from generation, from a variety of sources. But then you look at how is that generation going to be managed. It has to be managed in a way that data centers can use it, all the way down to the consumer, because he's going to want to be able to use it as well. We're talking about not just the availability of electricity, but the uninterruptibility of electricity that has to be there when you want it. And when you talk about generation, that supply is part of it. The question is, how is that managed? You can't have fluctuations at data centers. That doesn't work. You need to have storage. You need to have batteries and other forms of storage to make sure that the electricity will be there when it's needed. AI is something that's it's growing. The presence is felt by every human being, really on the face of the earth. If you look at your cell phone, you look at your MapQuest, that's AI, and that's AI right there. It has to be supplied by somebody, and that somebody has to be able to depend on the availability of electricity on a very uninterruptible basis. So the challenges out there are enormous. We have a growing need for electricity. We have a growing need for the efficient supply of electricity, the affordability of electricity, and the consistency of it to make sure that it can be there when we need it, and at a reasonable, affordable price. Also, sustainability. I don't want to forget that. That's also very important. So anyway, I think that's sort of the answer to your question there, but I would defer to the other guys as well.
One, we're seeing load growth in the U.S. for the first time in 20, 30 years. And up to now, what we've been doing really is we've been using high-efficient technologies to reduce grid load. Right now, we're seeing grid load because of EVs, because of data centers. Grid load is increasing. So we are going to continue to expect end-use technology to become more efficient, whether that's a heat pump or something like that. I mean, there's going to be some gains in efficiency, and also within the data center. But right now, we're seeing data centers in the 30, 40, 50 megawatt range, some in hundreds of megawatts. These are equal to steel mills historically. These are large loads. We see some people even talk about 1 gigawatt data centers. So clearly, we have to think about how we're going to manage that. And the power quality issue, the reliability issue it's not just getting the power, it's a high quality power that allows the data center to fully operate at its peak efficiency. And any small fluctuations, even sub-cycle, can cause the data center to have issues. So that's where a battery or some kind of energy storage can come into play and actually act not just as an energy storage solution, but a power quality filter. So we see some solutions there, but it really is a mixed solution where you're looking at hydro, you're looking at nuclear, you're looking at combined cycle, solar, wind. All of these technologies are generating energy, but they have to be at the time of needed use. So that's where you usually have a storage solution. Now, whether that's a battery, whether that's some kind of thermal energy storage, there has to be a storage solution, but it's also aligning that storage solution with a timely charge where it's efficient, where you're not paying a high rate, because you want that to operate on off-peak time, because you need the 24/7 reliability. But we're also thinking about, can we shift some of that data center load that's non-priority?
I kind of go back to my manufacturing roots in a lot of ways, where we focus on lean processes through our manufacturing facilities. And getting the lean process means you're pulling stuff in, you're minimizing your store size in between, and you're getting stuff out efficiently, right? If you end up with a huge over-design on the front end with a lot of extra power and you don't need it on the external side, that we've historically called waste on our systems. In the same way, I see that for data centers. So if you're going to go put in a 30 or 50 megawatt data center, and then you're going to average something like 20 megawatts on the data center, there's about 30 megawatts of waste on your data center. I see batteries being a really good application to help make up that differential. And if you do that with batteries, what you end up doing, though, is you end up really heavily cycling the batteries. Instead of cycling them once a day, you're continuously using them. I think from an architecture perspective, some chemistries take this better than other chemistries. And I think some battery architectures take it better than other battery architectures. This is one of the areas, right, where, I'm very excited about flow technologies where active material doesn't degrade, specifically around cycling. It allows you to have a really, really high durability system and a very fast response system that can help balance that DC voltage swing that you get from a data center load, specifically training loads, more than anything, where you see huge jumps that can exist in 30-40% of a data center in maybe 1 or 2 cycles of an AC current swing.
So AI is clearly a major priority for this administration, for the federal government in general, and I think it's reflected also in state governments and local governments that are all trying to bring some of these things together because people see that opportunity. So how do we stabilize the grid as it is today to address things like AI, which are challenging the grid, challenging our technology and our systems? How do we then optimize that grid? So get the most out of what we have, minimize areas where we don't, where you can improve the efficiency of the AI system, for example, or you avoid waste, and ensure that your power quality is good. And then how do you address future need to grow the grid to address things that we don't even know about today? I can tell you last year when I was here, the conversation was different, and I was only 12 months. So if you think about where AI has gone in that time frame and sort of the excitement around that, it's really pretty daunting and exciting at the same time. So energy storage is such a versatile tool. I'll put it this way. Energy storage is unlike any other technology we have. We confuse it with other technologies all the time, but it is unlike anything else in terms of what it can do, and that's the kind of tool you need to address the new challenges that we've never seen before. So I'm not saying it's going to solve all the problems, but I think it's absolutely essential to solving many of the problems that we're going to see.
After a couple of comments here alone, we've pretty much settled on the fact that battery energy storage systems going to be an essential component to AI data center processing, period. So we're going to kind of assume going forward that in the discussion that's part of the deal. Now, how do we get battery energy storage into the landscape so that it can help AI in many other places as well? So from a utility perspective, how hard is it going to be to integrate battery energy storage system into a utility landscape?
Over the past 20, 30 years or so, it's become more difficult to actually build generation in this country. It takes years, sometimes even decades, not just to build a power plant, but also the transmission that is needed to bring the power from the plant to the consumer. Not just transmission, but distribution. In the case of data centers, they can't wait that length of time to bring their power to their facility. They got to have it like tomorrow. And so you're seeing a lot of data centers build their own power facilities on site. Now, what does that mean for the utility? It means for one thing that they have to adjust the way they operate to the way the data centers operate. And this is forcing your data centers and the utilities to work together more closely than they ever had before, to the point where I think you're starting to see some of the power supplies that go into data centers also becoming available to the utility. When you see something like that, then you really get into the issue of power quality and power management, and you got to have batteries there. This is a wide open field for batteries to help utilities and the data centers work with each other to supply the needs for the consumer.
I think one of the challenges we're seeing is that interconnection time. What can be done to speed up interconnection? So when a data center builds out an asset until the grid can get there, because it needs to become operational before the traditional grid can get there, how can that asset then be flipped once the grid gets there to become a dispatchable asset?
Do you see a point where the data centers will have excess power routinely and basically be participating on the grid as a utility themselves?
I think one thing that's going to change as data centers start to add electricity on their own into the system is you're going to see data centers go for stuff like one-to-one power generation to demand sets. The grid historically has been able to leverage a massive overcapacity, right, which has helped reduce the load of variable frequencies on those assets. If the data centers are going for one or using near 1-for-1, they're going to see substantial issues unless they've got a massive battery in between them, right? Because you can't swing assets like that. You do get some momentum, right, with spinning assets, but that's really frequency based. It's not large scale momentum. You'll end up really harming mechanical things. The inertia also hurts mechanical things to stop. So I think as you see that shift, right, I don't foresee data centers being able to deploy a lot of their excess energy through generation assets to the grid. I think that they will be able to supply energy through their batteries to the grid. So I think only through over-design in a battery system would they be able to really start to deploy that, because other than that, they're not going to have enough overhead in their system.
Erik, is there anything we need from a regulatory point of view to help balance between what the data centers are producing and what the utilities are producing and help the coordination?
Part of what the challenge is right now is these are unprecedented challenges, right? We don't know what all the problems are. AI and the data centers, the hyperscalers are introducing problems that this generation of people on the grid have never even had to think about. The magnitude and the timing and the frequency of the changes that are coming in terms of what the impact is on the grid, both taking power from the grid and stopping taking power from the grid, those things really give utility folks a headache. So when you think about what the utilities actually are going to want, these are the most conservative people on the planet as far as I can tell. So they're going to want to see reliable power. They want things which are dispatchable, that are reliable, that they know what they have, when they have it, and when they're going to need it.
How do you see technology-agnostic behavior playing into the energy storage explicitly for AI data centers?
What are the features and the characteristics demanded by the application? And then the chemistry will eventually fit those, right? So if you ask me right now, I'm obviously invested heavily in the vanadium space. The vanadium space is a great technology because it works today, and we have a problem today, right? If I look 10 years down the road, I would expect that flow technologies will have proliferated, right? There will be other options out there associated with flow technologies, and they will continue to develop. As such, we will develop with them, right? I think right now, vanadium is the play for flow batteries, and I like that as an architecture to solve the AI data center problem.
My philosophy is emerging more and more these days is to say, what do you need for a particular situation in a particular place? And if you understand comprehensively what your needs are and how much you have to spend on things, you're basically going to find the solution. You're going to basically look comprehensively to say, I don't care if this battery can do X and Y better than this other one does X and Y. The point is this collection of power electronics and energy storage and generation and reconductoring and all of this other stuff that comes together is going to create a comprehensive solution that's going to allow you to meet all of the needs that are in this side of my equation.
Frank, I think EPRI is actually either sponsoring or part of some new deployments as well. What's in your basket that you're seeing?
Yeah, we're currently running a large number of demonstrations around some batteries and also some flexibility assets and trying different things with data centers. But I think you're absolutely right. You've got to find the right tool for that application. And then there's a cost question. Data centers are not inexpensive to build, and batteries are an additional cost to your compute. And, but one of the advantages to the battery is the battery may live longer than your compute. You may have to change out your compute technology before your battery. So sometimes you can start thinking about a technology that's a little longer down the road because it's going to have a longer lifespan. So it's a lifespan question, it's an application question, it's a chemistry question, it's a safety question, and it's a cost question.
So the testing, the demonstrations, things like what EPRI is sponsoring, things that the DOE is sponsoring, other things where we're putting these things out and we're trying to run them through their paces, boy, is that stuff important, because that's how you learn, here's what this actually is, rather than being defined by whatever is on the sticker, is to say, here's what it can actually do, then you know what you have as a tool.
I would say even speaking further into that, as we look at this problem and this stage domestically, right? This problem's actually a little bit larger, right? So actually supplying through domestic inputs and having a secured energy supply chain associated to where we are in the U.S. and being able to supply what are mission critical assets for the U.S. This technology train is a long ways off, right? If you look at virtually every BESS system that has been deployed in the U.S. are non-U.S. cells, right? So the supply chain today is really a long ways away from being a domestic supply chain, right? And I think that that is a challenge in a lot of ways, and I think it also is an opportunity for us as we start to look into where we can be as a country and as an industry.
Do you guys see a chance? We're talking about serving AI, making sure it's available and reliable to the broader community, to commercial applications, et cetera. Do you see AI actually playing a role in battery performance itself? Can you apply AI to batteries? It's kind of a self-fulfilling loop, right? You're making AI available through batteries, and then you use the AI to improve the battery. Is that a loop that we're going to start seeing?
There's two loops, at least two loops, right? So we can use the AI. We are already using the AI to figure out how to make the batteries better in the first place.
Yep.
So we're innovating new materials, we're putting together different systems, we're exploring data sets that help inform basically ways to actually improve the technologies themselves. Then you can also imagine that there's another loop that is already being explored today, and that is how do you use the battery or the energy storage system, whatever it may be, as part of a system, because there's so many parts that have to get plugged in. So towards that point I was trying to make about optimizing the grid, you get the most out of your generators, you get the most out of your transmission, you optimize when things are charging, when things are not charging, when you're dispatching, how do you relieve congestion on the grid, all of those things that are coming into play. And when you put a monster variable like AI on it, you're going to need AI to help figure out how to help AI.
Right.
Yeah, and I think you hit on a real key, and that's actual data sets. You have to have more assets in the field, giving you more data to build a better data set, which gets you more assets in the field to build a better data set. It's an iterative process, and in every generation we're going to learn something, and AI will make the next process better. But a key is also be able to get that data. So many times, we get into a situation where there's an asset out there, and maybe it's a proprietary data set, and we have to think of a way that we can become much more of a shared open model where we can get data, use that data to make the grid stronger regardless of the manufacturer, regardless of the technology, whether it's the generator, whether it's the battery, whether it's the, whatever that is. That data set is what's going to drive AI, because AI is not going to get better if we don't give it better data. And to get better data, we have to have more data.
I looked at a map of data centers throughout the world. Who's made the biggest investment in data centers? We have in America. And so that means that we're in a pretty strong position already in terms of developing an AI industry throughout the world. The rest of the world is trying to catch up with what we've done here. So I think we're starting from a pretty strong position already. The other thing I would point out about batteries is that America has had a very strong industry in batteries for well over a century. So yeah, AI, we're leading. And when it comes to energy storage, we got an industry right here that's done a fantastic job already. We've got a good foundation to move ahead on.